Hello everyone. Today I would like to introduce MetricCAD. It's a viewer for Prometheus exporters. First, let me briefly introduce myself. My name is Slava, and today I'm talking with you from Tokyo, Japan. I work in Line Corporation. We are making the most popular messaging application in Japan. And I do use Prometheus and Grafana on a daily basis. Let me start from introduction of some problem I faced. I was developing batch processing application. It was typical batch processing that runs for several minutes, and it had some problem in it. To solve this problem, I wanted to look at the internal state of this batch processing and how it changes in time. Luckily for me, I already had these metrics that I needed for debugging exposed as a Prometheus exporter. But how can I look at them in local environment? I came up with three approaches. First, I could deploy this batch application somewhere and use external Prometheus to scrape metrics for me. This is a little bit troublesome since I would have to deploy it every time I make a little change to the application. Second approach is to run my Prometheus locally, for example in Docker, and configure it to scrape metrics from my local application. That would require of setting up Prometheus locally and making sure it works correctly, which might not be a trivial task. The third approach is to scrape and visualize metrics manually. That's actually pretty easy to do since Prometheus is pool-based system, and MetricCAD can help us here. So please meet MetricCAD. It's an application that scrapes and visualizes metrics. It can work with both local and remote exporters. It can scrape metrics at any interval, and it has pretty simple UI. Let's look at UI. This is connection window, and you can enter the exporter URL here. It can be remote or local one. You can enter request interval at which the scraping will happen. And then you click start recording. After you click start recording, you will see this screen. This is main recording screen. Here you have the list of metrics on the left, some stats on the bottom, the start stop button on the bottom right, and in the main area you have some metric information such as name, description, type, and data for the selected period. It will update in real time. MetricCAD can be useful for local development and debugging. For example, if you develop exporter, or if you develop applications that supports instrumentation, or if you develop some or debug some functionality that exposes metrics through existing exporter. Also, you may take advantage of high resolution metrics. The normal Prometheus that you have running in your beta or production environment might have pretty high interval, let's say 10 seconds or 15 seconds. But for MetricCAD, you can set few seconds interval and have much higher resolution of metrics and have much better information to look at. And finally, you can export your metrics to file and share it with your colleagues, analyze with external tools. You can visualize it as you like. And finally, I would like you to go and try MetricCAD. So you can download it from metriccad.dev. It's only available for macOS at the moment. The Windows version is coming soon. Also, I update this application quite frequently, so please, if you're interested, subscribe for updates. You can do that on the download page by clicking subscribe button and entering your email, or you can use Twitter. It's MetricCAD Dev. Please follow that. So thank you for your attention and have a nice conference day.
So our next lightning talk is from Jürgen Etzelsoffer about fortifying progressive delivery with quality gates.
Hi everyone, my name is Jürgen, and today I want to talk a little bit about fortifying progressive delivery with automated quality gates based on data from Prometheus. So what is the actual problem we want to solve? And it all comes to your CI/CD systems, where you have manual approval steps where you actually want to approve some builds before they reach your production environment. And what is the problem here? And that's basically that this manual approval takes quite a lot of effort and time. So first you have to indicate, or you have to decide if something's going wrong, if it's really a real problem. Is the trend that you are seeing, is it enough data? You have to identify which build is better. Was the previous run better? Or was the actual, the current run better? You have to manually compare this based on some dashboards, based on some spreadsheets. So it's a lot of manual comparison, and the base problem might be that actually it's difficult to gather all this data from the monitoring solutions underneath that have all this data, and you have to make sure that you are providing your decisions based on the right data. So all this manual approval process can take quite a long time. So how can we solve this? And I want to give you a little bit of an idea how we are solving this within an open source project called Captain. So Captain can integrate in your CI/CD system. In this case, we've just sketched it with Jenkins, but you can use Captain to actually trigger the tests in your test environments with JMeter, with Neoload, with any other testing tool. Captain is an event-based framework, an event-based control plane, so to say, that can just trigger different tools to trigger the tests, and after the tests are finished, Captain again will be triggered to evaluate these tests. So Captain will do a quality gate evaluation based on the data. So it will fetch the data for the testing timeframe, and it will evaluate the data based on service level objectives. And after the evaluation, it will generate a total score, and based on the score, you can then decide if you want to push it to production, or if you want to just leave it there, or either roll it back, or just give an indication to your developers that this build was not successfully evaluated. So instead of having this manual approval process for 30 or 60 minutes, you can really compress this process to 1 minute. That's basically based on 2 different files that are used inside Captain, and this is a service level indicator and a service level objective file. So how does it work? We do have service level indicators. That's basically, let's say, a library of different metrics that are given a name. So like it's a key value pair, like an error rate, and the corresponding Prom QL, how to get this error rate for the service. This can also be parameterized, so you can reuse it really easily, and Captain comes with a built-in library based on the red metrics already. So you reuse this, but you can also come up with your own indicators, like, for example, the number of database calls. And then you can use those indicators inside of a service level objective file, and you will just define that, for example, the number of database calls is only allowed to increase by 2% to the previous runs. So that basically means for a given time frame, you're not allowed to execute more database calls than in the previous runs. Only 2% increase is allowed. That basically gives you gives you confidence in not having some regression in your different runs. But you can also compare it to absolute thresholds, like it's done here for the error rate, that has to stay lower than 1%. So with these 2 files, you can now trigger a Captain quality gate. And you can do this either with the Captain API or with the Captain CLI. You will start an evaluation by triggering a Captain quality gate. Captain will reach out to its SLI providers that can connect to different data stores underneath, like Prometheus or Dynatrace or Neoload, whatever tool that can provide you data about your test runs or the evaluation timeframe. So Captain will evaluate this data, will fetch this data, will evaluate the data, will score it, and will come up with a total score. And this might be like a very successful build, very successful test run, or it might be not so successful. And you will get the final result, pass, warning, or fail. And upon this, you can then act in your CI/CD systems. So you can see it's a very easy, but yet very, very powerful mechanism to include this into your CI/CD systems and to fortify your progressive delivery pipelines. Since it's only a matter of a couple of minutes for this evaluation, you can do this for canary releases, for blue-green deployments, because there is no actual effort and it doesn't take much time to evaluate the quality gates. So if you think this might be something for you, please check out our website. It's captain.sh. As said, it's an open source project. It can work with different data stores. We have our source code on GitHub. It's github.com/captain/captain. That's our main repository. So that's a good starting point to take a look at. If you have any questions, please feel free to reach out to me. I provided here some contact information, and have fun at this year's PromCon. Bye.
Okay, well, thank you. So next up, we have a talk from...
Hello everyone, my name is Sunku Ranganath. I'm a network...
From Sunku Ranganath, who's going to be talking about lessons from closing the cloud-native infrastructure loops. These all start playing as soon as I hit them. Okay.
Hello everyone, my name is Sunku Ranganath. I'm a network software engineer working for Intel. My topic today is lessons from closing the cloud-native NFV infrastructure loops. Here's the legal disclaimer. And thanks to the team that helped in making this work happen. Transformation towards network slicing across 5G networks and zero-touch service management require the infrastructure to be heavily automated, which is where closed-loop automation plays a crucial role. As indicated in Figure 1, key operations in a closed-loop automation-based system involve in identification, measurement, detection, and corrective action across various layers of NFV infrastructure and virtual infrastructure management, aka VIM. Cloud-native deployments need to be aware of runtime telemetry from the underlying infrastructure to perform low-latency scheduling and resource utilization decisions. Extensions such as Kubernetes telemetry or scheduler, horizontal pod autoscaler, or custom Kubernetes operators can help close the loop by leveraging infrastructure telemetry for workload management. Analytics methods can include streaming analytics or more traditional periodic collection methods, and insights can be generated using either method. The closed-loop resiliency demo indicated here highlights the importance of runtime telemetry and analytics within a Kubernetes cluster, and its impact on workload scheduling and migration policies. As described in Figure 2, analytics component leverage runtime telemetry from collectee collector across the nodes to trigger alerts from Prometheus Alert Manager. Platform telemetry like last level cache occupancy, cache misses, memory bandwidth, temperature, fan speed, etc. are used to calculate host health indicator by the analytics component. Kubernetes telemetry aware scheduler can then decide if workload needs to be migrated from node 1 to node 2 using alert levels from Prometheus. Zooming into the analytics component, Figure 3 shows the usage of streaming analytics via Kafka and KSQL to calculate host health indicator. The indicator is then scraped by Prometheus, and Alert Manager generates critical or minor alerts based on preset conditions. Kubernetes telemetry aware scheduler lets the workload continue running in case of minor alert, or can decide to migrate the workload to node 2 in case of critical alert. This demo hereby indicates the importance of software and hardware components involved in realizing a low latency closed loop scenario for infrastructure resiliency. When the demonstrated concept is applied at scale, there are a few important takeaways that help a cloud-native telco deployment. Number 1, platform telemetry beyond the usual CPU and memory metrics are crucial to minimize downtime and maximize service availability. Some of the key metrics include, but not limited to, CPU last level cache misses, occupancy levels, memory bandwidth, power and energy metrics, network interface metrics, corrected memory errors that indicate memory reliability, etc. Number 2, streaming analytics and runtime data processing closer to workload is important to take corrective actions for low latency closed loop scenarios. Finally, integration of Prometheus and Kubernetes telemetry where scheduler extensions help provide runtime resource availability-based workload management. Here are some more references to help you look into more details, and I'm happy to follow up offline for any questions. With that, thank you very much for your attendance today.
Okay. Thank you. Next up, we have Mate, who works on Timescale, who's going to talk about long tails everywhere, lessons learned optimizing relational schema for Prometheus data.
Hey, my name is Matt, and I work at Timescale DB on integrating Timescale as a long-term store for Prometheus data. Some people may ask, is it even possible to scale a relational database to support the high interest rate of Prometheus data? Well, you are right to ask because traditionally this has not been possible. But with Timescale DB, you can indeed store time series data in Postgres and support the high interest rates and volumes associated with Prometheus and metric data. In fact, we support hundreds of billions of metrics on a single box, have efficient time series compression, and this summer we will release a horizontally scalable version of the database. And now let me explain why you would want to do this. Well, in a word, support for SQL analytics. By adding SQL, we allow you to perform much deeper analytics, including arbitrary aggregates and OLAP rollups, joins with other data in your system, and integrations with existing tools for machine learning and predictive analytics. So how do we do this? The first question we had when designing the schema was whether we should put all metrics into one global table or split up metrics into separate tables. To answer this, we analyzed the data distribution of Prometheus data and found that the cardinality of metrics followed a long-tail distribution, where a few metrics had very high cardinality, but most had low cardinality. This motivated our decision to split up metrics in order to avoid performance interference between metrics with very different data distribution properties. This also allows us to optimize single metric queries, which we found to be much more common than the multi-metric ones. The second question was how to normalize tags. The issue is that tags are big because they contain a lot of long repeating strings. So you don't want to store them in JSON blobs. We came up with a normalized schema where the text for the keys and values of labels was normalized out into a separate labels table. And the series table simply contained an array of foreign keys into the labels. This avoids storing repeating text strings multiple times. But there was a problem with this implementation in that grouping by a particular label key, say namespace, became inefficient. Because you had to join every foreign key in your label array to the label table to find the one single label for the namespace key. That's a lot of joins. But we quickly realized that if you could just map a particular index in the label array to a label key, you'd be able to retrieve the identifier for a given key, thus avoiding all the joins to the label table. This also allows you to create easy-to-use views for people to query by aliasing particular label keys to columns in the view. Here are some examples of queries you could do on that view, which you wouldn't be able to do in plain Prom QL. You could take aggregates over both time and series simultaneously. You could calculate rollups and cubes, set permissions on particular metrics, perform joins with auxiliary data, and use more advanced statistical functions, even writing your own. There's much more info in the design doc, and feel free to email me with any questions. Thank you.
Hey, thank you. So our next talk then is from, I apologize for the pronunciation, Karupya Natharanjan, about smoothly upgrading exporters with breaking changes.
Today we're going to look at how to smoothly upgrade your Prometheus exporters which have breaking changes. So this talk came up to be because of some work that we did in our project around the start of this year. So we were upgrading our node exporters, and while doing this we noticed that there were some breaking changes, and we noticed this only when our Grafana dashboards were broken. So yeah, we started checking out what went wrong in our Grafana dashboard, and we found out that the obvious thing that can go wrong with an exporter, which is the difference of metrics. So the older exporter version had a different set of metrics, and the newer exporter version had a different set of metrics. So when I say different, there were some metric name changes, or some metrics were removed, and the same was happening for metric labels. So one example was node network transmit bytes was converted to node network transmit bytes total. So what we did was we did some manual work, and we also used some JavaScript code to find out the differences between the two versions. So and we created a map wherein we said if the old metric name is this, then the new metric name is this, if there is a breaking change. And we did the same for label names. And with that data, what we did was we downloaded the Grafana dashboard JSONs, which represent the Grafana dashboards, and we used bash scripts and changed the name, the metric names and label names in these. And we put back the Grafana dashboard JSON back in Grafana. And the scale of this problem that we had was only around some 10 to 15 Grafana dashboards. That's it. So we could afford to do some manual work and also use basic scripts. But soon we realized that if the scale of the problem was bigger, let's say you have a lot of exporters that have some breaking changes in your way, upgraded them, and you also have a lot of Grafana dashboards that need changes, then you would have to use some better tooling. So you could use something like a Golang tool, since Prometheus and Grafana are written in Golang, and you can tightly integrate with them and use the packages in them and do your work in a better manner. So I'll show a quick demo of one tool I built. So I have the node exporter version 0.15 metrics here, and for version 0.18. And if I run my tool for this, it shows me the difference. between the metric names. So these are the old metric names that are not present in the new version. So this is one such example, and you can build more tools for Grafana dashboard JSON changes, and the same for to upload Grafana dashboard JSON or to download it. And that was my talk. And one thing to notice, we faced this problem because our Grafana dashboards were custom built. And if you get your Grafana dashboard from the internet and you upgrade your exporter, you can also upgrade your Grafana dashboard by getting the newer version from the internet. So you wouldn't have this problem. And another way to solve the problem is just don't upgrade. But at some point you'll have to upgrade, yes. You'll have to see the cost versus benefit analysis, and the sooner you upgrade, it's better for you. Yeah. So that was my talk, and I'm Karupaya. I'm an application developer at ThoughtWorks, and you can reach me at karupaya7890 at GitHub and Twitter, and you can also reach me in my email at karupaya7890@gmail.com. Thank you.
Okay, thank you, Kripa. Our next talk is on
Hi everyone, my name is Dave.
A operational sandbox for Prometheus by David Grisanti.
And I'm going to talk a little bit today about a sandbox project for Prometheus that my team and I have been working on at Comcast. So I work on a team that's offering Prometheus as a service to developers at Comcast. And we follow a pull request model for our clients when making configuration updates to their Prometheus configuration in production. And this is a pull request to CI to production model. And this is as opposed to allowing users to SSH directly into the host to make their changes. And this oftentimes poses some configuration challenges with first-time users in getting their configuration correct. So a local developer setup doesn't mimic this environment oftentimes because they can't reach their desired targets in production due to connectivity. And like I said, we don't want anybody SSHing directly to test out these changes. So developers are oftentimes looking for more of a REPL experience where they can test out changes immediately and see what the experience is like, kind of like a read-eval print loop in a programming language environment. So if you see this example over here to the right, this is an example we often see where people are trying to pull hosts from AWS, filter on some tags, and then pull some metadata back from AWS to add to their metrics as labels. And first-time users don't often get this configuration correct. So they end up following the cyclical process of opening the PR, pushing the changes, having an error, and it just gets frustrating for them. So we built this small web app called PromBox that gives the users an area to play in production, but that's separate from their production instance. So it's deployed in the same AWS VPC or network zone, uses the same Prometheus Docker image plus client configuration, and it runs alongside Prometheus as a sidecar, so it has access to their shared file system. So let's jump into a quick demo. So here's the Prometheus PromBox UI. You see that the configuration is shown, and the users have access to edit this, so they can scroll, look at the whole config, and make changes. So if we try out just a simple change, like make the scrape interval 30 seconds and then save it, we can see that after saving, it will give us this message. And on the save, we actually are running Prom tool in the background and reloading Prometheus via the reload admin API. So if we try to add a new scrape job, let's say, but let's say we make a mistake, and when we save, we should get an error saying that the configuration is bad. And this kind of gives users that REPL experience I was mentioning before, where they can try out changes and see what the errors are without having to commit it via the pull request process. In addition to that, we also pull in some status information from Prometheus via the API. So this is similar things you find in the Prometheus UI, such as configuration rules, targets, etc. But to kind of fill that gap, we're still giving users the Prometheus UI directly via the frame option. So this is basically Prometheus in an iframe, and it's the same interface you would get with Prometheus and it is the local Prometheus that's running alongside PromBox, and you can see your targets and everything else here. So let's say we wanted to add a brand new target and see how that gets reflected on the targets page. So we can go back to PromBox, add the new target, save it, and what should end up happening is we see that new target appear. And the benefit of that is you can see how the new targets show up, and also like what labels are getting added if you want to do any kind of relabeling logic or things like that. And then you also have the ability to even see those metrics since we're showing the Prometheus interface here. So it's a pretty simple concept, but we have plans to expand this further by adding easier configuration of adding scrape jobs outside of just editing the YAML, adding new recording rules, and adding new alerting rules. So that's all the time I have for today. Thanks. And if you have any questions or just want to chat, feel free to hit me up on Twitter. My Twitter handle is in the lower left-hand corner. Thanks.
Okay. Thank you, David. Then our final lightning talk for today is from Rob Skillington on highly available metrics with M3 and Prometheus.
Hi, my name is Rob. I'm here to talk to you about highly available metrics with M3 and Prometheus. I'm the creator of M3 and a open metrics CNCF contributor. M3 is a remote storage for Prometheus. You can use a Kubernetes operator to deploy it into Kubernetes and scale it up and down, or you can use a single Docker image for tests. You can store metrics for weeks, months, or years with downsampling. You can store metrics at different retention based on different mapping rules, so optionally keeping some SLA stats for certain months or years versus your whatever else you keep your fire hose for. Allow for scaling high cardinality metrics by aggregating across dimensions that you want to keep at ingestion time rather than solely relying on recording rules, which always add extra load because you're querying them over and over again to produce a result. And M3 also allows you to scale out storage just by adding nodes, rebalancing the data using pure streaming. So it's really designed for zero downtime upgrades, restarts, and can withstand entire replica failures. You will always be able to read and write data no matter what, as long as 2 of your 3 replicas are up. So a single node goes down, that doesn't impact your visibility or insight into the system. It keeps on going and is highly available. So that's no matter whether you have 1, many, or all nodes down. M3 can also be deployed in a multi-region fashion and at query time join data across the regions if you want to keep your data local to a region to keep egress costs down. And at Uber, we really did have to focus on the scalability of this. It can warehouse and does warehouse more than 1 petabyte of metrics data there and stores 40 million data points per second. And so it's it's really only when you hit that second replica down do you see an impact in writes. You still actually have visibility in reads, but that's a side point. So looking at the aggregator and how that's reliable and what that lets you do, the aggregator is a streaming metrics aggregator, which optionally lets you keep all of your metrics downsampled. So that allows you to make your metrics less dense. So when you go to view them over months and years, both the query time is fast and the storage cost is much cheaper than keeping all the raw unaggregated data. It allows you to also create rollup rules, which can basically squash the cardinality of metrics down and move expensive recording rules to streaming aggregation to store less and alert on very high cardinality metrics cheaply. And it does this reliably by using etcd to transparently elect a leader across 2 availability zones or 2 replicas. And essentially, when it performs a failover, it will make sure anything that wasn't flushed before an aggregator went down is flushed by its follower, which takes over as leader. So diving into a specific example of a high cardinality HTTP latency metric, here we're going to track basically the status codes and the latency of 50 HTTP routes across 100 pods per region, the bucket tag, so say you have 30 buckets, status code tag, say we have 10 status codes, we're tracking 50 HTTP routes, 4 active server versions, and 4 regions we run in. If you add all these and multiply these unique values together, we get 24 million unique series. Essentially using an aggregator rollup, we can aggregate this in a streaming way at ingestion time down to 240,000 time series if we don't care about the pod label when we go to query or alert off these to get a high 10,000 foot view into these metrics. And you can still slice and dice by git SHA, region, route, status, and all that. And so, so that number going from 24 million to 240,000 series, if you're looking at a single HTTP route, you only need to touch like 5,000 time series now. So it's much, much faster. So breaking down how that actually works inside M3, basically we form this rollup rule on the right, which is valid YAML for a rollup rule inside M3. We basically take the increase of these original time series that are per pod. Then essentially we sum the deltas that we took per pod by the dimensions we actually care about, LE, git SHA, route, status code, and region. Then we get a resulting delta time series. Then essentially we do a running cumulative sum on these to get a monotonic counter based on the dimensions that we still care about. And then essentially, the summary here is this allows you to convert millions of time series to thousands. And it allows for very high cardinality metrics to impact your TSDB by performing constant query load the way that recording rules do. Recording rules are still super valuable. It's just that for some of these high cardinality workloads, it's definitely can be done cheaper this way. It optionally lets you drop in interesting labels and keeps the ability to apply further transforms. Thank you to all the M3 contributors. If you want to learn more, here are some links, and thank you for listening to my talk.